Now that we've gotten some experience applying Newton's second law to really simple systems, it's straight line motion of a single particle with a known mass. Let's back this out just a little bit and discuss some of the caveats around Newton's second law. And the main thing that we need to consider here is that Newton's second law doesn't apply everywhere. Now that may sound like a kind of a strange statement, but it's absolutely true. The application of Newton's second law depends wholly on your reference frame, or as we've defined before, the point at which you're observing the motion of what you're applying Newton's second law to. And so how Newton covered this in Principia Mechanica is that he said that you can only apply these laws when you observe the motion from absolute space. And so there's where that term comes in. Now, this fits along with some of the vagaries that he introduced, and we talked about a couple of those, which, force and mass, which he really didn't define, but he also took some pretty good heat after he published that as well. But with absolute space, he defined absolute space as being fixed to the stars, which, as we know, really doesn't mean anything in how we understand stars, because stars move. There's no such thing as fixed to the stars. So this has evolved into our current vernacular, in which we use reference frames, and we use something called an inertial reference frame. And I really can't emphasize this enough. If we're going to apply the laws of mechanics, we have to do it from the point of view from an inertial reference frame. Now, here's the thing about an inertial reference frame, is that it's an inertial reference frame, meaning that there's not only one inertial reference frame, there's an infinite number of inertial reference frames. And so that introduces another important idea of Newtonian relativity. And so Newtonian relativity is saying that there is more than one inertial reference frame. Any reference frame, and here it is, moving at a constant velocity and not rotating relative to another inertial reference frame, is also an inertial reference frame. So in the definition of an inertial reference frame, we have to have the idea of an inertial reference frame, and then we compare the motion between them, and that allows us to make observations. So what we are able to do is, once we define an inertial reference frame or locate an inertial reference frame, then we can test another inertial reference frame, and if it's moving at a constant velocity and not rotating, then it also is an inertial reference frame, and we can make our observations there and apply Newton's second law, the laws of mechanics, from that point of view. And so with all this talk about reference frames, let's turn our attention to the vector form of Newton's second law, so you can see it really in all its glory, in which we're emphasizing the reference frames, and here emphasizing the notation that we're going to use in this class. So take note of this figure, where it is in the book, but where it is in the notes. And if you ever have questions as we're dealing with reference frames and notation on what's a vector, what's a scalar, when we need to denote reference frames and when we don't, this is really invaluable because it shows everything that's here. And so what we see is we're back to where we started, which is Newton's statement, in which we have all the forces applied to a particle P. And so this is going to be the sum of all the forces. This is a vector quantity, so it's all the forces, all the force vectors added together that are acting on that particle, are equal to, and it's the time derivative, and this is the time derivative of a vector. And so it's the time derivative, and remember, if it's the time derivative of a scalar, it doesn't matter the reference frame that we're working in, but if it's the time derivative of a vector, it certainly does. And so we have to denote that we are observing this time derivative within a particular reference frame. For the laws of mechanics to apply, it needs to be the inertial reference frame I, and then back to Newton, it's the forces are equal to the time derivative of the linear momentum of particle P with respect to O, in which O is the origin in the inertial reference frame. And as we said earlier, it's mv. P is equal to mv, our linear momentum, and so our velocity is observed in an inertial reference frame. So it's the time derivative of the mass times the velocity as observed in the inertial reference frame. And so our general understanding of this is F equals ma, and so we see it in this expression where the right-hand side is equal to the scalar mass of the particle p multiplied times the acceleration of p with respect to o as observed in the inertial reference frame. And so that's how we speak about this. This is how we write about this, and you'll get used to this notation. But I really encourage you to visit this figure frequently. It's figure 2.2 in the Kasdan and Paley book. And when you have questions about clarity on what each of these elements might be.